In this section, we're going to generalize the notions of spans and linear independence. So a given set of vectors is said to be linearly independent if the given vector equation has only the trivial solution. And similarly, and if there is any non-trivial solution, then we say that the given set is linearly dependent. In that case, we can always find a linear dependence relation among each vectors. So we call that if the set of vectors contains zero vector, then they are linearly dependent. And if you have a set of two vectors such that one vector is a scalar multiplication of the other one, then it is linearly dependent again. So let's look at some examples. So suppose that you have three different vectors in a set of polynomials. So here P is the set of polynomials. Then P1 and P2 and P3 are linearly dependent because we can find a linear dependence relation. So for example, we have P3 of t equals to 4 minus t, but we can rewrite this as 4 times P1 of t minus P2 of t. So the set P1t, P2t, and P3t is not linearly independent. However, if the set is given by these polynomial, so the difference is we have square term here in P3, then in that case we have the set P1, P2, P3 is linearly independent. And this is because, so let's say you have a vector equation given by C1 P1 t plus C2 P2 of t plus C3 P3 of t equals to 0. Or in other words, this means C1 plus C2 times t plus C3 times 4 minus t squared equals to 0. Or if you distribute C3 into the parentheses, then you get negative C3 t squared plus C2t plus 4 times C3 plus C1 equals to 0. So if you take the derivative for the both sides, we get negative 2 C3 t plus C2 equals to 0. Then plugging in t equals to 0 gives you C2 equals to 0. And this, if you plug this back into that equation, then this gives you negative 2 C3 t equals to 0, or we have C3 equals to 0. And then lastly, if you plug this 2 into this equation, then we get C1 equals to 0 as well. So the vector equation only has trivial solution. So for this reason, we can conclude that the given set consisting of P1 of t and P2 of t and P3 of t is linearly independent. So the theorem 10 states that the set of vectors is linearly independent if and only if one of the vector is a linear combination of the other vectors. And it's very similar to what we have learned in several weeks ago. But the difference is, in this case, we can't necessarily write an augmented matrix because everything is in more general setting. Suppose that H is the subspace of a vector space V, then a set of vectors B is a basis for H if B is linearly independent and H is spanned by all the vectors of B. So let's see some examples about the basis. So suppose that E sub 1 through E sub n be columns of n by n identity matrix, or equivalently E sub i's are the standard unit vectors in Rn. Then are the columns of I sub n linearly independent? Well, I guess they're linearly independent. And this is because I sub n is an invertible matrix. And the span of the columns of I sub n, well, this equals to the column space of I sub n by definition. But this indeed equals to the whole space R to the n, and this is because if you take any vector b in Rn, then we can find a solution for this matrix equation I times x equals to b, where the solution is given by b in this case. So because this set is linearly independent set, and also they span Rn, so they form a basis for Rn. Does this make sense? Well, because the set is formed by the standard unit vectors, we call this as the standard basis for Rn. So we can generalize the argument above for an invertible matrix. So suppose that A is given by this, which is an invertible matrix. Then we know that, well, if A is invertible, then their columns are linearly independent. And we also know the span of the columns of A equals to R to the n. And again, this is because for any B in Rn, we can find a solution for this matrix equation where the solution is given by A inverse times B. And again, because the set is a linearly independent and spans Rn, they can form a basis for Rn as well. Now let us consider a set of polynomials consisting of all the monomials of its coefficient equals to 1. Then we are going to prove this set forms a basis for the set of polynomials with its degree less than or equals to n. So basically we have to check the linear independence and whether the given set spans Pn. So let's pause the video and try out these two exercises. Okay, so for the linear independence, suppose that you have a vector equation given by a sub 0 times 1 plus a sub 1 times t plus a sub 2 t squared and so on plus a sub n t to the n equals to 0. Well, then we know that the polynomial equals to 0 if and only if all the coefficients are 0. And also, for any polynomial of degree less than or equals to n, we can write f of t as, say, b sub 0 plus b1 t plus so on until b sub n t to the n. So from here, we can tell that the given set S indeed span Pn. So S forms a basis for Pn, and we call this as the standard basis for Pn. So here, the key idea for basis is that the bases are the most efficient or minimal spanning set of the vector space. So consider three vectors given in this way, and H to be the span of these three vectors. And let us find the basis for H. So first of all, we can observe that there is a linear relation between v sub 1 and v sub 2 and v sub 3. So if you calculate 5 times v1 plus 3 times v2, then you're gonna get v sub 3. So it seems like v sub 3 is kind of a redundant element to represent H. So we will show that the span of these three vectors are actually the span of these two vectors. And first of all, if you take any element W inside here on the left hand side, then we can write W as a linear combination of V1 and V2. So say C1 V1 plus C2 V2, but this equals to C1 V1 plus C2 V2 plus 0 times V3. So this means W is a linear combination of V1 and V2 and V3. Or in other words, W is an element of span of these three vectors. On the other hand, let's take an element W inside this part. Then we can write W as a linear combination of these three vectors. So C1 V1 plus C2 V2 plus C3 V3. But if you plug in linear dependence relation, into here, then this gives you C1 V1 plus C2 V2 plus C3 5 times V1 plus 3 times V2, and this equals to C1 plus 5 C3 times V1 plus C2 plus 3C3 times V2, or in other words, W is a linear combination of V1 and V2. So we've seen that V1 and V2 spans H, and what is left to show is to show these two vectors are linearly independent. But note that either V1 and V2 are not a multiple of the other. This means that V1 and V2 are linearly independent, so they form a basis for H. So the spanning set theorem states that if you have a set of vectors such that H is the span of these vectors, and if some vector v sub k in S is a linear combination of the remaining vectors in S, then even though you remove v sub k from the set, the vectors still spans H. Or in other words, we can remove a redundant element. And also, if H is not a zero vector space, then there is a subset S such that S is the basis for the given space H. So it is very interesting to find basis for null space and column space of the given matrix. So suppose that A is given by 4 by 5 matrix, and the RREF is given by that. Then let us first find the basis for the null space of A. So basically, an element x inside the null space satisfies AX equals to 0. And if you solve this equation, well, we have pivot position in here, here, and there. So we can tell that x1, x2, and x5s are basic variable. So we can tell x1 equals to negative x3 minus x4, x2 equals to negative x3 minus 2x4, and x3, x4s are free variables, and x5 equals to 0. Well, equivalently, the vector x can be written as negative x3 minus x4 minus x3 minus 2x4, x3, x4, and 0. And we can separate this by x3 times negative 1, 1, 0, 0, plus x4, negative 1, negative 2, 0, 1, 0. So from here, we can tell that, well, the null space is a span of these two vectors. So negative 1, 1, 0, 0, and negative 1, negative 2, 0, 1, 0. And we know that these vectors are automatically linearly independent. And we have seen this in the previous section. So the basis should be a set of these two vectors. So on the other hand, the basis vectors for the column space are a little bit trickier. So let's collect all the columns of A to form a column space. So the column space is given by span of column vectors of A, which is given by 1, 2, 2, 1, and negative 1, negative 3, negative 2, 2, and 0, negative 1, 0, 3, and negative 1, negative 4, negative 2, and 5, 5, 8, 2, and 1. So let's compare this with the column space of the reduced row echelon form. So if I copy the columns of the RREF of A, then this gives you 1, 0, 0, 0, and 0, 1, 0, 0, 1, 1, 0, 0, and 1, 2, 0, 0, and 0, 0, 1, 0. So if you look at the column space of RREF of A, then we can tell that this guy is a redundant vector, because if you add this with that one, then we get this. Also, we can get the fourth vector by adding this with 2 times the second vector. So we can easily kill these two guys. At the same time, note that if you add these two vectors, then you get the third one. And if you add this with 2 times the second one, then you can see that you will get the fourth one as well. So that way we can kill these two vectors. So basically the point is the essential vectors for spanning set really follows those on the spanning set of the RREF of A. So in this case, the basis for the column space of A is that three vectors given by 1, 2, 2, 1, and -1, -3, -2, and 2, and 5, 8, 2, and -1. Oops, it should be just 1. So in conclusion, the pivot columns of a matrix A in fact form a basis for the column space of A.